Hi everyone, I am Dr. Hang Ding from IU South Bend and I am teaching programming with Go. This is our first lecture of topic 1.3 composite types. And this is a very short lecture because we will only cover structs and pointers. The lectures of topic 1.3 are based on the following materials which you should read. The first material is from a tour of Go, more times structs, slices, and maps. And here is the link to that part of this Go document. The second materials include part of chapter 4 and chapter 1 from the textbook by Donovan and Kennigans. In particular, it includes section 1.2 and 1.3 from chapter 1 and the first 4 sections of chapter 4. Now let's start with discussing pointers. Go also has pointers, as in C, C++, and Java. Recall that a pointer holds the memory address of a value. In Go, the type written as an asterisk or star followed by a time t is the data type for a pointer to a t value. The zero value of the pointer type is always nil. For example, here we declared variable p to be of type star int, which is a pointer to an int value. So variable p can hold the memory address of any int value. We can also generate a pointer using the ampersand operator. The operand of the ampersand operator is any non-pointer variable, and the ampersand operator generates a pointer to its operand. For example, suppose we have declared variable I as an int variable and assigned to have value 42 using the short variable declaration. Then we can apply the ampersand operator to variable I by writing ampersand I, or just place the ampersand before the variable name I. So here variable I is the operand of this ampersand operator, and the expression ampersand I is a pointer to variable I. In other words, ampersand I is the memory address of variable I. Because ampersand I is a pointer to an int value, it has the same data type as a variable p, which has been declared to be of type star int. So we can assign ampersand I to p. The opposite operator of the ampersand operator is the star operator, which denotes the pointer's underlying value. The operand of the star operator must be a pointer, and the result of the star operator is the value being pointed to by the pointer operand. For example, suppose variable p has been declared as a pointer to int, as in this line. Then the star p is the value being pointed to by the pointer p. In fact, star p is an unnamed variable whose memory address is held by pointer p. So star p is like any variable of type int, and you can read the value from that variable or change the value of that variable. If p has been assigned to ampersand I as in this assignment, then star P is the same as variable I. So printing out star P in this case is the same as printing out the value of variable I. And assigning 21 to star P is the same as assigning 21 to variable I. But note that unlike C, Go has no pointer arithmetic. Pointer arithmetic is the set of valid arithmetic operations that can be performed on pointers. An arithmetic operation that can be performed on pointers in the C language is to add an integer to a pointer. But that doesn't work in Go. For example, in this program, we declare variable P to be a pointer to an int value. We do something with P. For example, we assign the memory of an int variable I to P. Then we try to add the integer value 2 to the pointer P. This would work in the C language, but it doesn't work in Go. As we try to compile this program, we got this error message. It said invalid operation P plus 2 mismatch times star int and untyped int. That is because here 2 is an untyped int and P is a typed star int, and you cannot you cannot add two numbers of different type in Go. Now we switch to discussing the first composite data type, which is struct. A struct is a collection of fields. To define a struct in Go, we write the keyword type, then the struct name, then the keyword struct, and then a list of field definitions inside a pair of braces. The keyword type is to define any data type, and the keyword struct indicates that the type being defined is a struct. In the field list, each field is defined with the field name followed by its data type. Each field definition is in one line. For example, here we define a struct named vertex with two fields named x and y, and both fields are of type int. So now vertex is a data type, and of course it also has values just like any data type. A struct literal denotes a newly allocated struct value by listing the values of its fields separated by commas. For example, this expression starting with the struct name vertex and followed by the list of field values 1, 2 is a struct literal of the vertex struct, where the field x has value 1 and the field y has value 2. A struct literal is analog to a constant integer of type int. Note that in a struct literal, if the closing brace is in a separate line, then you need to write a comma after the last field value. And since vertex is a data type, you can also declare variables of this type. Here we declare variable v of type vertex using the short declaration statement by assigning v to the vertex literal vertex 1, 2. You can access struct fields using the dot operation. For example, to access the value of field x in the struct value stored in variable v, we write v.x. You can modify the value of the field x in v as in the statement v dot x equal 4, or read the value of the field x in v as in the statement print ln v dot x. When writing a struct literal, you can list just a subset of fields by using the name colon syntax when name is a field name. In such a case, the order of named fields is irrelevant. For example, you can write the vertex literal in the assignment for the variable v2 by writing vertex with x colon 1 in the list between the braces. So here we don't specify the variable y, the field y, and this assignment statement is the same as is of this statement. So it's the same as assigning v2 to the vertex of y0, comma x colon 1, or v2 equal vertex of x colon 1, comma y colon 0. You can also leave the list of field values empty in a struct literal, but still need to write the braces after the struct name. Then the struct literal will have 0 value for each of its fields. And if you place the ampersand before a struct literal, then it returns a pointer to the struct value. So this assignment statement makes P a variable of type star vertex, that is a pointer to vertex. To access the field x of a struct when we have the struct pointer P, we could write star P in parentheses dot x. So here the star or asterisk is the dereference operation, which allows us to get the underlying value that the pointer P is pointing to. And the underlying value of P is a struct value. So we can use the dot operator to access the field x of the struct. However, that notation is cumbersome. So Go permits us instead to write just p.x without the explicit dereference. Here is an example demonstrating how to access a field of a struct from a struct pointer using this shorthand syntax. This example also shows how to use struct and pointers to implement a linked list. The data type of a node in a linked list is the struct node with two fields, data and next. The type of the field data can be any data type, but here we use int for simplicity. The type of the field next is a pointer to node. This program creates a linked list of two nodes, and the pointer head is pointing to the first node. So here we declared a variable head to be a pointer to a node with 0 value for its fields. So after this declaration and assignment, the node pointed to by the pointer head could have 0 value for the field data and the null value for the field next. So now in the next two statements, which are assignments, we modified the field data and the field next of the struct pointed to by the pointer head. So here we assign one to head.data. So it modifies the value of data in the first node from 0 to 1. And then we assign head.next to another node which has value 2 for the data field and value new for the next field. And we can also print out head.next, which is the same as printing out star head in parentheses dot next. We have learned all basics of pointers and struct in Go. Now let's explore some building structs in a package image because we will use this package in many examples later. Package image defines many useful structs. Two of them are struct point and struct rectangle. The struct point is the same as the struct vertex in our previous example. The struct rectangle has two fields, min and max, which are of time point. This defines a rectangle whose top right corner point is max and the top left corner point is min. So to create a rectangle, we just need to define its min point and its max point. For example, here we create a rectangle with the min point having values 0, 0 and the max point having values 10 for x and 25 for y. Recall that since rectangle and a point are defined in the package image instead of our old program, so we have to write the package name and a dot before the struct name when we want to use these structs. For example, here we have to write image.rectangle instead of just rectangle, and we have to write image.point instead of just point. Another package related to the package image is the package image/color. This package defines structs for color, such as the RGBA struct, which has 4 fields RGBA of type uint8. RGBA represents a traditional 32-bit alpha pre-multiplied color. The RGB fields represent the red, green, and blue components of the corner, respectively. And the A field represents the alpha value, which specifies how much it obscures whatever is behind it. Note that the image package also defines a struct of the same name, RGBA, but it represents an RGBA image instead of an RGBA color. We will come back to these structs in our examples later. Thank you for watching, and I'll see you again in our next lecture, which is part 2 of topic 1.3.